In data science, linear algebra is the engine under the hood. Linear algebra allows us to perform vectorized operations on entire grids of data all at once without having to loop through the data individually. In this tutorial, we're going to be looking at some of these linear algebra concepts in Python. On the screen, we have a small infographic. Call linear algebra functions, np.dot, for performing matrices multiplication. They also use we can also use np.matmul, short for matrix multiplication. np.dot can also be used for dot product, same as add operator. And then for some matrix operations, we have transpose, inverse, determinant. Numpy performs this operation very quickly. For those of you who might be familiar with how to perform this operation manually, I think you can testify to how pretty involved they are. And then for solving linear equations, we have eigenvalues and vectors. What is it? So for eigenvalues and vectors, for those of you who are familiar with the raw equation, for the values of lambda, those are going to be the eigenvalues. And then for every value of lambda, that is for every eigenvalue, there is a solution for v here, according to this equation. And that solution is going to be the eigenvector. But then when we do this in Numpy, it's quite fast and straightforward because Numpy handles the heavy computation for us. Anyway, let's get into Numpy. We also have this, I think, least squares, singular value decomposition. Okay, we're going to be looking at some of these concepts in this tutorial. So we're inside IPython. We're familiar with vector. We're familiar with what is it called? We're familiar with matrix. So we know that a vector is a column of data, and then we know that a matrix, it's a 2D array, or better yet, we might think of it as a spreadsheet. Okay, so we're going to start with dot product. For dot product, we're going to look at how we might multiply two arrays. So we're going to start with two 1D arrays, and then we're going to take it from there. So if we have A, we could have np.array, and then here we can have 1, 2, and then B, we can have np.array. I'm going to do 3, 4 here. So we can do the dot product by doing np.dot, and then we can pass A and B here. And this is going to multiply what we have here. So it's going to get the dot product, multiply, and then add together. So 1 times 3 is 3 plus 2 times 4, 8, which is 11. That's what we get. Then let's do matrix product. So this is just vector. So we can have A, and then we could have, okay, let's have this, can work with this. And we could have B. I want to do two 2D array. and then we're going to look at 2D and 1D later on. So here we can have a first row 5, 6, the second row 7, 8, like that. So then we can do the dot product, much like we did here, where we did what did we do? We did np dot dot, and then we did we pass the array like that. Okay, so we did this. We could also do a dot b. It's another variant. We could also do a at b. That's another variant. Okay. I think we could also do np.math mode, and then here we can pass a b. So the same thing. So you see all the different approaches we can use to implement dot products. Okay. What if we had we could have for instance, we could have x equals np dot array. We could have it to, okay, let's say we have 1, 2, 3, and then we have 4, 5, 6. Okay, so this is going to be 2 by 3. Okay, now we can do something like x at np dot ones. So we can multiply x by one D array comprising of 3 ones. So the key here is the number of columns here has to be the same as the number of rows that we have here. Otherwise, the calculation will fail. So if you look at here, we have 3 columns, 1, 2, 3, 1, 2, 3. So it's a 2D array. So when we do x dot product of np dot ones, the size is 3, so it's getting us a 1D array comprising of 3 ones. So this should give us a result. Okay, so we get the sum. Yeah, we get the sum. I'm coming. If you do x dot shape, okay, what I should have done is x. So this is x, and then for my np dot ones, when I did 3. All right, so this is what we get. So what this is doing is it's multiplying. Yeah, okay. So so we got 6. So it's doing 1 times 1 plus 2 times 1 plus 3 times 1. So that is 6, although it's presenting the result as floating points. And then we went ahead and did this 4 times 1 plus 5 times 1 plus 6 times 1, which is 15. So it's getting 15 points as floating points. Okay. I think that's that. We can do for transpose, which is one of our linear algebra concept. Transpose, we're going to look at transpose inverse determinant. Okay, now for transpose, we can do a equals np dot array. So let's try this. Let's add one more row. Let's do this to be 5. Sorry, 5, 6, like that. So if you do a, so now we have 3 rows, 2 columns. Now when we do transpose, what transpose does is it turns our columns into rows. So we can do a dot t. That's how we do transpose. Okay, so now we went from 3 by 2 to 2 by 3. 2 1, 5. So our columns have become rows. We can look at inverse and determinant. So you know that inverse is used to solve systems of equations like finding coefficients in linear regression. And then determinant tells us if a matrix can be inverted at all. Okay, so to implement inverse and determinants, what we're going to do is we're going to import inverse and determinant. That is the two namespaces from Numpy. So we can do from Numpy, Numpy dot linear algebra. Then we want to import inverse and then determinant like that. Okay, I think I've what's that? It says no module. Okay, I think I blundered the spelling. Forgive me. Numpy dot linear algebra. Then we want to import inverse and determinant like that. Okay. Now let's have C. Okay, we can work with this. C equals np dot array. Then we have now when we have C, so that's 2D arrays, 2 by 2. That's a square matrix. Now to calculate our inverse, we can use this INV namespace that we import from INV namespace that we import from numpy.linear algebra. So is it method now, if you like? So or function. So you can do INV, and then we can pass our array in here. So this is going to get us the inverse of the array, which is straightforward if you ask me. Because if you were to do the inverse of this manually, for those of you who are familiar with matrices operations, okay, we can also do for determinant C. So this gets us the determinant minus 2 points that. Okay, let's do for Eugen values and Eugen vectors. What is it? So this is Eugen values and Eugen vectors. In situations where we have a workable solution, where our solution is not trivial, that is when I think, is it when v is not equal to 0 now, if I'm correct? But in any case, we're going to get some set of values for lambda, and then those are going to be our Eugen values. And then for each of these solution we get for lambda, there is a corresponding solution for v as well, and then those are going to be our vectors. But then NumPy implement this very quickly, and the way it does that is we do from NumPy dot linear algebra. We can import EIG. So we had C before now, C this, and then we can do the Eugen values, Eugen values, and the Eugen vector for this matrix C. So we can do EIG C, that's it. And then when we do H values, which is going to be the values of our lambda, and then let's do for huge vectors, which is going to be the values of our v. Okay, so we get 2 by 2 floating point array. All right, so what else can we do? Now let's look at how we might implement these concepts in machine learning, specifically linear regression. Let's look at two linear equations, like two simultaneous linear equations. For instance, let's look at if we have 2x. Let's play with this. We can play with this. 2x plus y equals to 8. Then x plus 3y equals to 9. We know how this is calculated. We get, what is it called? We get a matrix. We look for x and y, then equals to constant 8 and what is it called, 9. And then we get, to find our constant, we're going to have the inverse of our matrix, multiplied by the constant, I think, if memory serves me. So the first thing we're going to do is we translate our coefficient of x and y to matrix, and our inverse as well. It becomes a 1D array, and then we can use Numpy linear algebra to solve this equation. So let's get into it. We can have A, so we have an np.array, and then here the coefficient of x is 2, so that's 2. Coefficient of y is 1. The second row, 1, 3. So 1 for coefficient of x here, 3 for coefficient of y, like that. So that's going to be our first matrix. Then our second matrix, we're going to have np.array, and then here we're going to have 8, 9. That's for our constants. Okay. Now we're going to use linear algebra to solve this, which is quite straightforward. So we can use solution equals, this is like a cheat code for those of you in high school. We can quickly use Numpy to check for the solutions for your linear equation, linear simultaneous equation. It might even be 3 by 3. This is 2 by 2. Yeah, it can be, you can have a 3-dimensional array. So you could have x, like 2x plus y plus something z, and then that's going to leave us with 3 constants. If you know what I mean, those of you who are familiar with this in matrices. Anyway, we could have, so we have np dot linear algebra dot solve. That's it. That's how we solve this linear equation. So okay, now let's print the solutions for our x and y. So we can do print f, then we do f string, then we can do x equals just pass the value here, solution that's going to be index 0, and then y equals just pass the value here, solution index 1, like that. Let's see what we get. So x is 3.0, y is 2.0. Okay, let's go back to the equation and verify. So 2 times 3 is 6, plus 2, 8. 3 plus 6, 9. Okay, so that's correct. What else can we do? We had what did we have the other time? All right, we've done for this. What else can we do? What about ordinary least squares? Another concept in machine learning where we can look at what is it called? This normal equation. So the other time we solve this linear equation, these linear equations, and then we look for x and y. There are other concepts in machine learning where solving for x and y doesn't just get the job done. We have to, especially in linear regression, we don't just solve for x and y, we solve for the weights. That is the coefficient that best fits a line to a cloud of data points. So, for instance, if we had more data points than variables, that's an overdetermined system. We can't find a perfect solution, so we find the one with the least error. So the formula for implementing that is known as the normal equation, which is this normal equation. So we have the inverse of transpose of x multiplied by x. So sigma equals inverse of transpose of x multiplied by x. Then everything multiplied by the transpose of x multiplied by y. This configuration is not quite right. So there should be another bracket here. So because it's everything here, inverse of this, everything multiplied by this, two entities here. So let's look at how we might implement that in Numpy. So we can do, let's go back here, and then we can do, let's have, I'm going to do x, and then we can do np.array. So here we're going to create dummy data, for instance, house size versus price. And then for array x, which I'm trying to create now, we can have the size in square feet. And then since we are creating dummy data of house price, house size versus price, if I do x to be size in square feet, that is the size of the houses in square feet, then perhaps I might do y to be price in I don't know, specific currency. So for x, which is the size of a house is in square feet, you can do array, and then first row, let's have 1,400 square feet. Second row, we can have 1, then 1,600 square feet. Third row, we can have 1,700 square feet. And then another row, we can have 1,875 square feet. And then let's have one more, then 1,100 square feet. And you might be wondering, why are we preceding this array with 1, 1, 1? So the 1 in array x, it represents the intercept, that is where the line hits the y-axis. Okay, now let's create our array for our house prices. So that's going to be y equals np.array. Okay, then we could have let's see, maybe 245 dollars, 312 279 308, and I don't know, 199. Okay, so 1 2 3 4 5, 1 2 3 4 5. Okay, good. Remember, we're trying to calculate for our weights. All right, so, and then we're using this normal equation, this. So let's see how we might work this into Numpy. We can have a inverse of transpose of x. Let's do that first. So this is x transpose of x. The inverse of that, inverse of transpose of x. Does this get it done? So np.linearalgebra.inverse. Okay, so we're looking for inverse of transpose of x. Okay, so we get transpose of x. This is not quite right. So it's going to be x at, so that's transpose of x multiplied by x. That's the dot products. So and we're using np.linear algebra inverse. Okay, so that undoes that gets that done. So guys, this is the first part, this part, inverse of transpose of x multiplied by x. So this is it. Okay, and then let's implement the second part, this one, transpose of x multiplied by y. So that's going to be x transpose y. So to do that, we have x transpose dot product y, this y. Okay, now let's get the weight. Weight is just this multiplied by this multiplied by this. Okay, so I think that's it, this multiplied by this. So that should give us our weights, and then we can print f string, and then we can do intercept let's pass weight index of 0, and then maybe we want to format fixed to floating points. Okay, so our intercept is 46.06. Let's get our slope. Print f, and then slope. Our slope, which is price per square feet. Price per square feet. That should be passed in the value, weight, and then this is 1. We can also format to floating point like that. And let's see what we get for our slope. So price per square feet 0.14. Whatever currency we're using, dollars, whatever. Now this is particularly important for things like optimization, scaling, even scaling. I think, yeah, let's just leave it like that. I don't know, should we do one more? I think I've covered everything here except least squares and singular value decomposition. Maybe we should leave that to when we get into machine learning proper. Okay, let's leave that. When we get into machine learning proper, we're going to look at least squares and single value decomposition. But I think I've covered some of the popular concepts in linear algebra here. So guys, that's all for this tutorial. I'm going to see you the next video. Thanks for watching.